Once upon a time, the universe was slowing down. At least, that's what every physicist believed. Gravity pulls everything inward. It should have been the cosmic break. But they were wrong, because something invisible and silent is not pulling, it's pushing. It is stretching the universe like taffy, faster every moment. Not with violence, but with persistence. We can't see it, we can't touch it, and yet it fills more than 2/3 of all that exists. It is the most powerful force we know nothing about. We call it dark energy. To grasp how shocking dark energy was, we need to rewind to the 20th century. When Edwin Hubble proved the universe was expanding, scientists assumed that over billions of years gravity would slow that expansion. Maybe it would halt. Maybe, one day, it would reverse into a big crunch. That was the comforting story. The cosmos breathes out, then back in. Symmetry. Order. Then came 1998. Two rival teams, each skeptical of the other, set out to measure how fast the universe was slowing down. They looked to distant type I supernovae, massive explosions so bright they can outshine a whole galaxy. Because their brightness is uniform, astronomers use them as cosmic mile markers. The result? They were dimmer than expected, farther away than they should have been if the universe were merely coasting. Something was making the expansion speed up. They had accidentally discovered not deceleration, but acceleration. Imagine throwing a ball upward, feeling gravity slow it, only for it to suddenly speed up and vanish into the clouds. Impossible, unless a hidden force was pushing outward. That invisible pressure received a placeholder name: dark energy. A quiet revolution had begun. Section 1A, Einstein's big mistake. Almost a century earlier, Albert Einstein had inserted a fudge factor into his equations, the cosmological constant. He needed it to keep the universe static because the idea of expansion sounded absurd at the time. When Hubble proved the universe was expanding, Einstein called it his greatest mistake. But in 1998, that mistake became genius. The cosmological constant was reborn as the simplest form of dark energy, a built-in pressure of space itself. Section 1B, Why It Matters. This discovery rewrote the cosmic ledger. Roughly 5% ordinary matter, 25% dark matter, 70% dark energy. The smallest part, the visible, is what we've spent all of human history studying. The largest part is the part we can't even define. Dark energy decides the fate of everything. We know what dark energy does. It pushes. But what is it? Three leading ideas compete for that answer. Section 2A, the cosmological constant. The simplest idea, space itself carries energy. Even the vacuum seethes with quantum fluctuations, particles appearing and vanishing like foam on a quantum sea. Each tiny fluctuation adds a little energy. Add up all of them, and you get a repulsive pressure that drives expansion. That's Einstein's constant reborn, a steady, unchanging energy density. If true, the universe's acceleration will continue forever, slow, steady, inevitable. Imagine an infinite fabric with microscopic springs woven through it. Everywhere you stretch it, the springs push back equally. But there's a catch. The calculated vacuum energy from quantum theory overshoots observation by 10 power 120 times. The worst theoretical mismatch in physics. Either our math is wrong, or the universe is playing a very fine-tuned game. Section 2B, Quintessence, the dynamic field. What if dark energy isn't constant at all? What if it evolves, like a field slowly rolling down a hill in the background of the cosmos? Physicists call this idea quintessence. Unlike cosmological constant, it can change with time. If it weakens, the universe's acceleration could slow or even reverse in the far future. If it strengthens, everything could end in a catastrophic big rip where galaxies, stars, and even atoms are torn apart. Think of quintessence as cosmic weather, a pressure system sweeping across the universe, its intensity shifting over billions of years. Future missions like Euclid and Roman Space Telescope are built to watch this weather, measuring whether dark energy truly stays constant. Section 2C, modified gravity. Or maybe there's no new energy at all, just new gravity. Einstein's general relativity has passed every test in our solar system, but perhaps it bends differently over billions of light years. Theories like F, R, gravity, brain world cosmology, and MOND propose subtle changes that can mimic dark energy's push. If those models succeed, what we call dark energy might be nothing more than a sign that our cosmic map is incomplete. It wouldn't be the first time. Newton's gravity ruled for centuries, until Einstein refined it. Maybe it's Einstein's turn to be refined. Section 2D, how it actually works. Dark energy doesn't push galaxies through space like wind on sails. It expands the space between them. Imagine dough hashrisin. Galaxies are raisins embedded in it. As the dough expands, the raisins drift apart, not because they move, but because the dough grows. Closer galaxies remain gravitationally bound. Our Milky Way and Andromeda will still collide. But across cosmic distances, space itself multiplies, pulling clusters apart faster than light can bridge them. The universe isn't exploding outward. It's growing its own emptiness. Section 2E, philosophical pause. Every generation of science peels back the sky and finds we know less than we thought. Dark energy may be a constant, a field, or a sign we misunderstand gravity. But whatever it is, it reminds us that mystery still sits at the center of reality. And perhaps that's the most beautiful part. We've seen what dark energy might be, but how do we know it's there? What's the actual evidence written across the sky? In the next chapter, we'll read the universe's oldest light, the cosmic microwave background, and learn how astronomers prove dark energy's fingerprints are real. Dark energy isn't an idea born of imagination. It's an idea born of evidence, written not in textbooks, but in the sky itself. Because the universe keeps a memory. Every photon, every ripple of gravity, every flicker of starlight carries a timestamp of the cosmos becoming what it is. Let's read that record. Section 3A, supernovae, the cosmic yardsticks. Our first clue came from those distant type I supernovae, brilliant explosions marking the death of white dwarf stars. When a white dwarf siphons too much matter from its companion, it ignites in a thermonuclear detonation so consistent in brightness that it serves as a standard candle. If it looks dimmer, it's simply farther away. But when astronomers compared brightness versus redshift, the data curved the wrong way. Instead of slowing, the universe's expansion was accelerating. This wasn't a fluke. Two separate teams, using hundreds of supernovae across billions of light years, found the same pattern. It's like watching cars on a highway, expecting them to decelerate, but seeing each one pull away faster. These results were so unexpected that scientists spent years checking every possible error. Dust, calibration, bias, selection effects. None changed the outcome. By 2011, the discovery was so robust that it earned the Nobel Prize in Physics. So our first line of evidence came from dying stars. Explosions that whispered the cosmos was not slowing down, but speeding up. Section 3B, the cosmic microwave background. CMB, the afterglow of creation. The second line of evidence comes from the oldest light in existence, the cosmic microwave background. This faint radiation bath, discovered by Penzias and Wilson in 1965, is the echo of the Big Bang itself. Photons released when the universe was just 380,000 years old. Satellites like COBE, WMAP, and Planck have mapped this radiation with exquisite precision. What they found was astonishing. Tiny temperature ripples, 1 part in 100,000, encoding the seeds of all galaxies to come. By studying the geometry of those ripples, we can tell the overall shape of the universe. The data shows it's nearly flat. But here's the twist. Visible matter and dark matter together don't provide enough energy density to make the universe flat. Something else, something like dark energy, must make up the missing 70%. Imagine measuring the curvature of the Earth by horizon lines. If the horizon looks perfectly straight, you know there's hidden mass keeping it that way. Dark energy plays that hidden role, flattening the universe's large-scale geometry. In the faint microwaves of the sky's oldest light, dark energy leaves its invisible signature. Section 3C, Baryon acoustic oscillations, the frozen echoes of sound. But the universe didn't start silent. In its youth, it rang, literally. Back when matter and radiation were mixed, pressure waves rippled through the hot plasma, like sound waves through air. These oscillations froze when the universe cooled and atoms formed. Billions of years later, those frozen ripples became visible as slight preferences in how galaxies cluster, a faint pattern called baryon acoustic oscillations, BAO. When astronomers measure the spacing of galaxies, that pattern acts as a cosmic ruler. And when they compare that ruler's length at different times, they see that the expansion rate changes faster, faster, faster. That's dark energy at work, written not in one galaxy, but in the entire web of cosmic structure. The same silent push that dimmed the supernovae and flattened the CMB also sculpted the large-scale universe we inhabit. 3 independent lines of evidence. 1 invisible cause. Section 3D, how the numbers add up. When cosmologists feed all this data, supernovae, CMB, BAO, into the same model, the result is stunningly consistent. 68 to 70% dark energy, 25 to 27% dark matter, 4 to 5% ordinary matter. That balance fits every major observation to date. We don't see dark energy directly. We see the trail it leaves, the way space behaves, the way light stretches, the way time itself accelerates. It's like hearing the hum of a distant engine you can't locate, but knowing from its vibration that something immense is running. Section 3E, the sound of the expanding universe. If we could compress the story of the cosmos into a soundtrack, it would begin with the deep bass of primordial sound waves, rise into the crescendo of galaxy formation, and end in a slow, fading hiss, the expansion accelerating into silence. That's what we observe today. Galaxies drifting apart like notes, fading into distance, their pitch stretching lower as space itself elongates the wavelength of light. The universe isn't just expanding, it's changing key. Section 3F, transition to next chapter. From the death of stars to the first light of creation, every piece of evidence points the same way. An unseen force governs the universe's evolution. But evidence alone isn't enough. The next question is why? Why does dark energy exist? Is it truly constant, or something that evolves, waxes, and wanes like a living field? In the next chapter, we enter the theoretical battleground, where physics meets imagination, to confront the theories and tensions of dark energy. Every great discovery in physics begins with excitement, and then meets a wall. Dark energy solved one mystery: why the universe's expansion accelerates, only to open a dozen others. What is it truly? A property of space? A field? An illusion born of misunderstanding gravity? Or perhaps a clue that our universe isn't the only one? Let's enter the storm. Section 4A, the cosmological constant problem. Einstein's cosmological constant, lambda, is the simplest explanation. Empty space itself has energy. But here's the nightmare. Quantum field theory predicts that every quantum field contributes a vacuum energy, a background hum from particles flickering in and out of existence. When physicists add up all those contributions across known fields, they get an absurdly large number. Not twice too big, not 1,000 times too big, 10 to the power of 120 times too big. That a 1 followed by 120 zeros. the greatest mismatch between theory and observation in all of science. If that predicted energy were real, the universe would have blown itself apart before atoms could even form. It's like calculating the weight of an apple and getting the mass of a galaxy. This mismatch is called the cosmological constant problem, the vacuum catastrophe. It tells us that something fundamental about how quantum mechanics and gravity fit together is missing. Section 4b, quantum vacuum versus reality. So why doesn't a vacuum energy annihilate us? There are three main possibilities. 1. Fine-tuning. The universe's true vacuum energy is incredibly small because positive and negative contributions cancel almost perfectly, a cosmic coincidence. 2. Unknown symmetry. Some deep law we haven't discovered forces that near-perfect cancellation automatically. 3. Anthropic selection. Out of countless possible universes, we exist only in one where the vacuum energy happens to be small enough to allow stars and life. That third option touches a nerve because it whispers of the multiverse again. If space-time inflation produces infinite bubbles, each with random vacuum energies, then only in rare ones does life appear. We, of course, live in one of those rare oases. Some scientists call that anthropic reasoning. Others call it surrender. Section 4c, the multiverse connection. If the multiverse exists, the cosmological constant might not need an explanation, just a context. Imagine an endless field of universes, each with a different vacuum energy. Most are sterile. A few, balanced just right, last long enough for galaxies and observers to emerge. In that case, our small, quiet cosmological constant is not strange, it's inevitable. As Steven Weinberg once said, it's not surprising we live in a universe where the cosmological constant is small. If it weren't, we wouldn't be here to notice. Weinberg used this argument before dark energy was discovered and predicted roughly how small it should be. When observations confirmed it, even skeptics took notice. It was eerie. The multiverse, once philosophy, had made a quantitative prediction. Section 4d, dynamic dark energy quintessence. But maybe dark energy isn't constant. Maybe it changes. In this view, dark energy is a field that evolves over time, a kind of cosmic fluid rolling slowly down an invisible potential hill. Physicists call it quintessence, from the ancient Greek word for fifth element, beyond earth, air, fire, and water. If quintessence is real, the acceleration of the universe might not be uniform. It could slow, halt, or even reverse. We can describe it mathematically by its equation of state, W. If W equals -1, it's the cosmological constant. If W minus 1, it changes gently over time. If W minus 1, we get something stranger, phantom energy, where expansion grows without limit until everything is ripped apart. That's called the Big Rip scenario, a haunting end where even time disintegrates. We don't yet know which equation the universe has chosen, but we're listening. Section 4e, modified gravity, changing the rules. Some physicists argue dark energy doesn't exist at all. They suggest we're seeing a side effect of how gravity behaves at immense distances. Einstein's equations might be incomplete. Theories like F, R, gravity, DGP brainworld models, and massive gravity propose small corrections that only matter on cosmic scales. They can mimic the acceleration without invoking a mysterious energy. How do we know which is right? We test how galaxies cluster, how gravitational waves move, how light bends around cosmic voids. Every deviation is a clue or a trap. Section 4f, observational tensions. Today, the data mostly fits CDM, the model with a constant dark energy and cold dark matter. But cracks are appearing. Measurements of the universe's expansion rate, called the Hubble constant, don't agree. Local measurements give one value. Cosmic microwave background data gives a lower one. This Hubble tension may signal systematic errors or new physics lurking behind dark energy. Another tension arises from the growth rate of cosmic structure. Galaxies seem to cluster a little less than our models predict. Again, either coincidence or a hint that dark energy evolves. It's as if the universe is trying to tell us something, but in a whisper we haven't yet learned to decode. Section 4G, the philosophical dilemma. Dark energy sits at the crossroads of humility and hubris. It shows how little we know, that 95% of the universe is invisible to us, and yet we dare to model it, name it, even argue about its personality. Maybe dark energy is a window into quantum gravity, the bridge between Einstein and the quantum realm. Maybe it's the universe's way of keeping secrets until we're ready. Every discovery carries a question it cannot answer. For dark energy, that question is destiny. If the universe is expanding faster and faster, what becomes of everything we know? Will the stars go out quietly, or will the cosmos itself be torn apart? To see the future, we must follow dark energy's fingerprints to the end of time. Section 5A, the Cosmic Balancing Act. For decades, cosmologists imagined three broad fates for the universe, depending on its total energy content. 1. Closed universe, the Big Crunch. If gravity dominated, expansion would eventually slow, halt, and reverse. Galaxies would collapse back into a single, fiery singularity. The cosmos would end where it began, in fire. 2. Open universe, eternal expansion. If expansion overwhelmed gravity, galaxies would drift apart forever, stars would die, and space would grow cold and empty. 3. Flat universe, perfect balance. Expansion and gravity would balance at infinity, slowing asymptotically but never stopping. For most of the 20th century, cosmologists debated which we lived in. Then dark energy entered the equation and rewrote every ending. Section 5B, the Big Freeze. If dark energy is truly constant, the cosmological constant, then expansion will continue forever, accelerating but never ripping space-time apart. In this future, galaxies drift beyond each other's horizons. Over tens of billions of years, their light fades and redshifts into invisibility. Each island of matter becomes isolated, cut off from the rest of the cosmos. Stars exhaust their fuel, leaving behind white dwarfs, neutron stars, and black holes. Even those decay through Hawking radiation. After an inconceivable stretch of time, 10 power 100 years, black holes evaporate into photons. The universe becomes dark, silent, empty. Imagine a candle burning in an infinite void. It doesn't go out in a gust. It simply fades until the wax, the wick, and even the light are gone. That's the Big Freeze, the slow death of everything. The ultimate triumph of entropy. The quietest apocalypse imaginable. Section 5C, the Big Rip. But if dark energy's strength increases with time, if its equation of state W is less than -1, we face something far more dramatic, the Big Rip. In this nightmare, the acceleration keeps rising. First, galaxy clusters are torn apart, then individual galaxies, then solar systems. A few billion years before the end, the Milky Way dissolves. Minutes before the end, Earth's atoms rip from their electrons. A fraction of a second before the end, even space-time disintegrates. Nothing survives, not matter, not light, not time. It's not fire or ice, but disintegration itself. The universe, unmade by its own expansion. Some models suggest this could happen tens of billions of years from now. Others, never. It depends on the true nature of dark energy. Section 5D, the Big Crunch and Big Bounce. Not all roads lead outward. If dark energy isn't constant, if it weakens or reverses, the expansion could slow, stop, and reverse, triggering a big crunch. Galaxies would rush back together, temperatures would climb, and space-time would collapse into an immense fireball. Some theorists extend this idea to a big bounce, where the collapse triggers a new Big Bang. In that view, universes rise and fall in eternal cycles, each universe born from the ashes of the last. It's speculative, but it's poetic, and it reminds us that endings and beginnings may be the same event viewed from opposite sides of time. Section 5E, the time frame of eternity. How long until any of this matters? Not soon. In 5 billion years, our sun becomes a red giant. In 100 billion years, galaxies beyond our local group fade from view. In 1 trillion years, star formation ends. In 10 superscript 1 years, the last stars die. In 10 years, even white dwarfs and neutron stars fade. By 10 superscript 1 years, black holes evaporate. After that, only photons and lonely particles remain, coasting through a featureless infinity. Section 5F, the emotional horizon. It's hard to speak about these scales without losing meaning. 100 billion years, 10 to the 100 years. Numbers so vast that language itself begins to fail. But within that silence lies a strange comfort. We, tiny, fragile beings, have lived for less than a heartbeat of cosmic time, and yet we already know how the story might end. We are part of a universe that can think about its own death. No other phenomenon we know of can do that. Maybe that's what makes life precious. That meaning exists not because it lasts forever, but because it burns so briefly against eternity. So the universe will end, not with a bang, but with expansion. Whether by freeze, rip, or collapse, its fate rests in the hands of an invisible force we still don't understand. But we're not done, because before we accept our ending, we must be sure we've measured the story correctly. New missions, Euclid, Roman, DESI, LSST, are mapping the sky in ways never before possible. Their goal, to pin down dark energy's nature once and for all. In the next chapter, we travel into the future of observation, the cosmic instruments that will rewrite the destiny we just imagined. The story of dark energy isn't over. It's just begun. Every great mystery in science begins as poetry, becomes a problem, and ends as precision. Dark energy is now crossing that threshold. Section 6A, the new eyes on the sky. Across the world and above it, a new generation of cosmic instruments is coming online, each one built for the same purpose: to measure how the universe accelerates. 1. The Euclid Space Telescope, ESA 2023. Orbiting 1 million miles from Earth, Euclid is mapping billions of galaxies up to 10 billion light-years away. By measuring how they stretch and cluster, it can track the influence of dark energy over cosmic history. 2. The Nancy Grace Roman Space Telescope, NASA 2027. Often called Hubble's heir with a wider eye, Roman will measure supernovae and weak gravitational lensing with stunning accuracy. It will test whether dark energy's pressure, its equation of state, truly stays constant or shifts with time. 3. DESI Dark Energy Spectroscopic Instrument. On the ground in Arizona, DESI is already capturing the light from 35 million galaxies, turning each into a time capsule. It's the largest 3D map of the universe ever attempted. 4. LSST Legacy Survey of Space and Time. Under the southern sky in Chile, the Vera C. Rubin Observatory will photograph the entire sky every few nights for a decade. By comparing millions of images, it will reveal how cosmic structure evolves and whether dark energy changes its grip. Together, these missions are like a symphony, each instrument tuned to a different frequency of the same truth. Section 6B, Precision Cosmology, Measuring the Invisible. The age of precision cosmology has begun. We no longer ask, is dark energy real? We ask, what is its nature? How stable is it? Does it interact with matter or itself? By measuring redshifts, distances, and the bending of light, we can infer how space-time curves, how expansion changes, and whether the laws of gravity still hold. Every pixel of a galaxy, every distorted lens, every dim supernova becomes a data point in the story of the universe's destiny. Section 6C, the quantum gravity frontier. Yet, even with better data, a deeper riddle remains. To truly understand dark energy, we must unite two incompatible giants: quantum mechanics, the physics of the very small; general relativity, the physics of the very large. Each works perfectly in its own domain, but when you put them together to calculate the vacuum energy of space, the math explodes. That is the cosmological constant problem in disguise. The solution will likely come from a theory of quantum gravity, a framework that merges the two into one coherent picture. String theory, loop quantum gravity, holographic models, all are trying to bridge the gap. Somewhere in that bridge lies the truth about dark energy. Section 6D, the philosophy of progress. Science has always been a dialogue between ignorance and curiosity. The more precisely we measure the universe, the more mysterious it becomes. When we mapped the solar system, we found galaxies. When we mapped galaxies, we found expansion. When we mapped expansion, we found dark energy. Every time we draw a boundary around knowledge, the unknown grows around it. That's not failure. That's progress. Section 6E, hope in the infinite. So yes, the universe may end in darkness, but between now and then lies eternity's dawn, and we are here for its first light. Perhaps that's our purpose, to witness, to question, to leave behind understanding. If dark energy is the force that drives the cosmos apart, then curiosity is the force that pulls us together. The one energy in the universe that defies entropy. Section 6F, the bridge to the next mystery. Dark energy makes up 70% of everything, but it's not alone in the shadows, because another invisible presence threads the universe like a skeleton shaping galaxies, anchoring clusters, guiding light. We call it dark matter. If dark energy is the expansion, dark matter is the structure. One pushes, the other holds, and together, they decide what the universe becomes. If this journey made you think, binge the Cosmic Mysteries playlist, subscribe to NetraVerse, and share this film with someone who stares at the sky and wonders. Because the more we learn, the more the universe looks back, asking us the only question that truly matters. What will you do with your moment beneath the stars?